Hi, this is Precalculus Section 1.2, Functions and Their Properties, Part 1. This year in Precalculus, I intend to deliver most, if not all, of my lectures via video, such that watching the video before class, you can come back the next day and get in with the exercises. And the exercises associated with this will be the videos titled Precalculus. It'll say Chapter 1.2. And so this is the title you're going to look for the videos associated with this. And I have Part 2 coming up later, and the reason I've separated this into two parts is this is really a crucial conceptual unveiling to really understand what we're covering in Precalculus this year. The first thing we're going to look at is the nature of a function, and this is a function machine. The machine has inputs coming into the machine and an output going out. And so what you're doing is you're taking numbers and taking some kind of a formula or algorithm and creating an output. And a key feature of the function is functions have to be one-to-one. And I'm going to demonstrate what that means. In this case, you have example A. These are called mappings, these four examples. And if you have an input, that input is only going to go one-to-one possible output. And so A goes to D, B goes to E, C also goes to E, but that's okay because you still have a one-to-one situation. And likewise, for example, C, you have A goes to R, C goes to Q, and D goes to S. But over here on the right, you have examples of one-to-many situations. For example, A goes two different places, to D and possibly also to E. And then in example D, you have A is mapped to P, but also to R. And likewise, B is mapped to P and also to R. So you don't know what you're getting. So in this situation here on the right, it would be like you're going to a vending machine, and when you enter your money and press the button, you're not exactly sure what you're going to get. That is not a function. Whereas these examples on the left would be of functions. Next, algebraically, does the formula y equals x squared define y as a function of x? And what you're looking for is if you have an input value for x, are you only going to have one possible output value? And so you can just try different numbers. If we try -2, we're going to get -2 times -2 would be equal to 4. If we enter 0 as an input to this equation, we get 0 as an output. If we put in +2, we will likewise get 4 because 2 times 2 is 4. And 3, input of 3, output of 9. And so no matter what real number we put in for x, we're only going to get one possible output value. So therefore, this would be a function. Now, if we said y equals plus or minus x, now this would be an example of something that is not a function, because this thing could be either y equals x or y equals -x. So this one here would be not a function. Whereas y equals x squared would be an example of an equation that is a function. Next, graphical examples of relations. Are these functions? Well, there's something that we can use. It's called the vertical line test to tell graphically if a relation is a function. And what you do with a vertical line could be anything. It could be a pencil, a finger, a sheet of paper. In this case, I have this little wooden stick. if you take the graph and go left to right, and the graph touches that vertical line at only one place, you have maximum, you have a function. So this is an example of a function. Here, this one below, you have a relation consisting of points. Only touches once, touches once, touches once, touches twice. Not a function. This example here, lower left, not a function. On this one on the upper right, touches once, but then once you go beyond that, you have not a function. So this could be like plus or minus square root of x. Y is plus or minus square root of x. This bottom one here touches this curve. Looks like kind of a sine curve. Talk about that later. Only once maximum. A function. So function, function, not. Next, find the domain of a function. Well, a domain is the possibilities for x values or input values for this function or equation. So we're going to do this algebraically and graphically. So we know that we cannot take the square root of a negative number. So you could, for instance, if we want to take the square root of 2, or square root of negative 2, is that possible? No, it's not, because there is no number that we can multiply by itself twice to get negative 2. So this would be does not exist. The situation would not exist as a real number. And so we know that anything inside a radical cannot be negative. So in this case, we take what's under the radical, x plus 2. X plus 2 cannot be negative, so we could write that as greater than or equal to 0. And then if we just solve this inequality, we can subtract 2. We have x has to be greater than or equal to negative 2. So that's an algebraic solution. Now, for this next function here, g of x, you have two situations going on simultaneously. One is that you have in the numerator this x, and x has to be greater than or equal to 0. But also we have this in the denominator, and we know we cannot divide by 0 in math or in algebra, so we would say that x minus 3 cannot be equal to 0. And this is another inequality. If we add 3, we know that x cannot equal 3. And so we can base our domain on this. And for the last one here, a of x, well, this one here, let me go back. You have two situations simultaneously. You got x has to be greater than or equal to 0 except cannot be 3. And we're going to write this in something we call interval notation in a second. The last one here, a of x equals square root of 3 over 4 s squared, where a of x is the area of an equilateral triangle with side length s. Now, if we didn't have all this wording here, if we just ignored all this wording, our domain would be all real numbers because there would be no restrictions. But to have a triangle, what do you have to have? You have to have a length of a side. You cannot have negative length. So in this case, we would say that s would have to be greater than or equal to 0. I guess, well, you could even say greater than 0 because you just have a point if it's 0, if the side length is 0, and you start to have a triangle when the side length is greater than 0. And we can represent all of these domains in something called interval notation. In interval notation, we take a break to explain what that is now, in that you may not yet be familiar with that. Well, interval notation is just a way of describing a domain in this case. Well, in this case, you have x is greater than or equal to negative 2, so we would write that as negative 2, comma, infinity and closing with a parentheses. And so this bracket means that x can be -2 or greater up to, but not touching, infinity. So this is an example of interval notation of this situation here. And now for this g of x function, we know that x has to be greater than 0, greater than or equal to 0, and can go up to infinity, but not quite. But there's a break at x equals 3, so we can go from 0 to 3, and we can go from 3 up to, but not including infinity. And what we'll do for this is we'll place a u, and this u is called a union. And so we use the union u to represent where we have different pieces of a function that we want to piece together. And then for the last one, we have this s is greater than 0, so we would represent its domain here by 0, infinity. Okay, so we would say on the interval or on closed interval from -2 to infinity, closed interval -0 to open interval 3 union, open interval 3, infinity, closed interval infinity, open interval infinity. So anyway, that's just a brief introduction to something we're going to be using all year and beyond. Interval notation. Next, graphically, what we've done here is have the graphs for these functions, and the first one is the graphical representation of this f of x equals square root of 20x plus 2. So here we have the function greater than, we can see at -2 is where the thing really starts to exist and goes up toward infinity. The next one, this one right here, this function, the graph of this function is a representation, and we can see, I hope, that x equals 3. I place a dotted line, so the function is never going to be defined at x equals 3 because of this restriction. So we talk about restrictions to our domain. And the last one we have is this one, and this is a graph of this function here, except because we have to have positive length, we know this whole part of the curve on the left is excluded. So our domain graphically is going to be represented by this graph to the right of our y-axis. Next, finding the range of a function. Well, there are some tricks to finding a range of a function, but at this stage in precalculus, generally we're going to examine the range of functions graphically. You graph the function, see what it looks like, and here's the function graphed. F of x equals 3 over x, and you can see that the range of a function is going to be greater than -infinity up to, but not including 0, union not including 0, but up to less than infinity. So this is an example of the range of this particular function. Next, continuity. And here is a shot that shows 5 different possibilities for continuity. Continuous, a function continuous for all x, a removable discontinuity. Another example of removable discontinuity, a jump discontinuity, an infinite discontinuity. And we're going to break these and look at them in more detail. Continuous for all x, meaning that from -infinity up to not including positive infinity, we have continuity all the way. So one way to look at it graphically, if you can take a pencil or a pen and not have to draw your pen or pencil off the paper, that would be an example of how you'd have continuity all the way. And so what we would do for this, how we would represent this in interval notation, we would say our domain is going to be greater than negative infinity, less than infinity. And sometimes you might have seen this kind of script R thing for all real numbers. Verbally, we'd call this all real numbers. Sometimes you see these all reals to abbreviate, but that's what that looks like. Next, we have a removable discontinuity, and here we have the function looks like the last one, except right here at our input value of a, but we have f of a here defined, so our domain will be defined over its entirety, just like the last one, but will not be continuous. So negative infinity all the way to infinity, and at a, you have a point that breaks the rule, if you want to call it that, but still has all real numbers as its domain. Next, we have another example of removable discontinuity where it's similar to last drawing, except at a, you have a discontinuity, but you also do not have a place to fill in for it. And so what we call this for a domain, we would go from greater than negative infinity all the way to a, input of a, but not including a, union a, comma, infinity. So that's what this domain would look like for this particular situation. And removable discontinuity, anytime there's just a single point that you could fill in and make the function continuous, that would be a definition of a removable discontinuity. And of course you may have the question, what is a non-removable discontinuity? We will see that example right here. Okay, the domain, this is a jump discontinuity. That's the type of discontinuity we have at this point, because the function comes all the way here to input of a. Our domain is still defined for the entirety of input possibilities, so we're still negative infinity, comma infinity, but we cannot fill this in. We cannot just fill this in this point and make this a continuous function by filling in a point. And so this is an example of a non-removable discontinuity. Okay? Next, we have an infinite discontinuity, and an infinite discontinuity is represented by what we call a vertical asymptote. Vertical So the vertical asymptote is what graphically we see that represents there's an infinite discontinuity. We would also say this is a non-removable discontinuity. And our domain would be similar to what we saw last, which is negative infinity to a, but not including a, union a to infinity, to less than infinity. So those are the situations we're going to cover. I so happen to have a discontinuities t-shirt that has representations of the three main types of discontinuities: an infinite discontinuity with vertical asymptote, a point discontinuity like we saw in one of our sketches, I think the second and third one, where we're only discontinuous at a point Otherwise, the thing looks just like a regular function. And finally, we have an example of a jump discontinuity, where the function will go along with one rule, then jump to another one. And so all the synonyms are here. We're going to go over those in more detail during the course here the next couple of weeks. Increasing, decreasing. And here's an example. This is the back of that t-shirt I have. And we say the function is increasing from negative infinity, here interval notation, up to x equals negative 1. So negative infinity up until x equals negative 1. And then also from x equals 4 toward infinity. And decreasing only on this interval. Now, a lot of mistakes are made by saying, well, the function is increasing from negative infinity to negative 2. And then again from negative 1, 2, 3, 4, negative 5 to infinity. No, what we say where the function is increasing has to do with x values. So that's why we have it this way. And now some examples. Here's an example of a function that is increasing for all x. So we say this function is increasing, I'll just put INC, on, meaning on the interval of negative infinity, greater than negative infinity, to less than infinity. Next example, we have this function here, which is one that's decreasing. So we say decreasing on negative infinity, greater than negative infinity, less than infinity. So that's this particular example. And then you can have an example where you have a constant example. So this is a constant function, and this is one of y equals 4.5. And we say this function is constant on the interval negative infinity, infinity. Okay, so there we have an example of a constant function. And then we have an example like this, where you have a mixture of intervals. So the function value will be decreasing. We'll say decreasing on negative infinity, and you're looking for the x value. Not the y value would be 1, but the x value is negative 2. So decreasing on that interval, and constant on the interval, we're going to have negative 2 to x equals 1. And finally we have increasing on x equals 1 to less than infinity. And I know arguments can be made, like you can say that, well, if things increasing, you could, from 1, you can actually make a bracket that actually from 1 on, the thing is increasing. That's a debatable thing, but that's going to be an argument for another time. And so really, that's all we're going to have in this section here. And this will enable you to do about half the exercises in section 1.2, and we're going to have part 2 that's going to explain other key concepts. Good luck, and thanks for viewing.